The previous lecture video ended with the promise that we would develop a problem-solving method for relating a force working on an object to the resultant change in kinetic energy of the object. We can start with the idea that we have an equation for kinetic energy and we have an equation for work or working done by a force. Note that in this working equation, we are taking the integral from point A to point B as a force is exerted on an object along a path from A to B, and we're taking the integral of that force dot dr. But remember that a force is a mass times dv dt, mass times acceleration. I'd like to point out here that dv dt dot dr is going to tell us the same thing as dr dt dot dv. That little bit of algebraic manipulation will tell us the same thing. This puts us in a position where we can replace the dr dt with v, that is the instantaneous velocity of an object. So the work done on an object, or the working done by a force, is equal to the integral from A to B of mass times the instantaneous velocity dot dv. That integral means I need to evaluate 1/2 times the mass times v in the x direction squared as I travel from A to B, plus v in the y direction squared as I travel from A to B, plus v in the z direction squared as I travel from A to B. While those are vector quantities, the magnitude of the vector sum of the velocity in x and y and z is the speed, and that speed goes into the kinetic energy equation, 1/2 mv squared. So if I'm evaluating this from A to B, that is from an initial point to a final point, then I can establish that the work done by that force is mathematically equal to the change in kinetic energy from point A to point B, from initial to final. And this is called the work energy theorem. The problem-solving strategy that is on this slide is directly from the OpenStax textbook, and it is an excellent way to work through any problem that is trying to get you to relate a change in kinetic energy to working being done by a particular force. Specifically, it says to draw a free body diagram for each force on the object in question. I'd like to remind you that we've been doing this for some time, and we're not moving away from it just because we're moving into the scalar mathematics of the work energy theorem. So you will start with the free body diagram every time still. You will evaluate whether each force acting on the object does work over the displacement that is shown in this particular problem. If you're not sure, then do the calculation, and the working may come out to be 0 joules. As it says here, you add up the work done by all the different forces, keeping track of what's positive, what's negative, and of course what's 0. And as I said in class, that will be equal to the working done by the net force, which is not an actual force. The net force is the vector sum of all the individual forces. So we want to make sure that we're clear when we say the working done by a net force. What we mean is the net result, the net work done by all of the individual forces. That net work should be equal to the change in kinetic energy if you've done your mathematics correctly. This is an example that's given in the OpenStax textbook of how you might want to relate a change in kinetic energy to the working done by a force. They are showing you a bullet striking a series of boards. The bullet is initially traveling 335 meters per second. On the picture on the right, it shows the bullet poking out a little bit on the far right side, but that's not meant to imply that the bullet actually leaves. It's brought to a stop right there. So you know the kinetic energy final of the bullet is 0, and so the relationship between the initial kinetic energy and the working done becomes a relationship between the mass and speed of the bullet initially and the force exerted to stop the bullet over the certain distance that they're giving you, the stopping distance. Let's work through a couple of examples, specific examples, to make sure that I'm being clear about how you would do this. In this example, we're given a 30 kilogram crate on a conveyor belt, and it is being pushed to the right by some force applied of 120 newtons, and we see a frictional force pushing to the left, 5.0 newtons. They show us the force of gravity pulling down and the force normal pushing up, and we are to believe that those two are equal magnitude but in opposite directions, so there will not be any acceleration in the y direction. And so the example might be asked, which forces are causing acceleration of this box as the box is moved 0.800 meters to the right? Which forces are causing a change in kinetic energy of this box, and which forces are doing work during the motion of this box to the right? Well, for the first question, you might say the force applied is causing an acceleration of this box. I would note friction is also causing an acceleration of this box. The wording of that sometimes throws people off. So the real question we're asking is, which forces are having some effect on the velocity of the box and how much the velocity of the box is changing? So the force applied and friction are both doing that, which means the force applied and friction are both causing a change in the kinetic energy of this box. Which forces are doing work must therefore be the force applied and friction. What you might be realistically asked to calculate in a problem like this is a series of questions like these. How much work is done by force applied? How much work is done by the frictional force? What is the net work done on the box? What is the increase in kinetic energy over the distance, d equals 0.800 meters, and how fast is the box going after this distance? In part E, I would assume that we are starting at rest, although I don't think it says so initially. How much work is done by the force applied over that distance of 0.800 meters would be found with that equation that we have used before for a constant force applied over a distance. The work is the dot product of that force applied and that distance. And since these two are pointed in the same direction, the theta between them is 0 degrees, cosine 0 is 1. So this just becomes 120 newtons times 0.800 meters, and we get 96 joules. How much work is done by friction over the distance is found with the exact same equation, but of course now friction is 180 degrees opposite direction from the direction of the box's motion d, so we would have to cosine 180 degrees in addition to multiplying the 5 newtons times the 0.800 meters. And so I get that that is 4 joules of work done by friction, but that is negative. So what is the net work done on the box? Well, the weight of the box and the normal force we didn't calculate because those forces are exerted perpendicular to the displacement. They each do 0 joules of work. So the net work on the box will just be the work done by the force applied added to the work done by the force of friction. That is 96 joules plus negative 4 joules, meaning 92 joules of work is done on the box. What is the increase in kinetic energy over the distance? 92 joules. I know that because of the work energy theorem. How fast is the box going after this distance? Well, I would say if we start with the assumption that the box is initially at rest, then its initial kinetic energy is 0 joules and its final kinetic energy becomes 92 joules. So I can determine the speed of the box from the 92 joules kinetic energy final, and I get that the box is moving 2.5 meters per second at the end of this trip. You can double check that if you want by determining the net force, and from that finding the acceleration, and from that finding B final using kinematics, and you'll get the exact same answer. So if it's the exact same, why are we learning a new way to do it? The answer to that is more obvious in problems like this one. The work energy theorem and the scalar mathematics done with energy become very useful in situations like the one shown here, where the force acting on the object varies over the course of its motion and or where the path is difficult to analyze. So we're initially going to be using problems where we could have done it using kinematics and Newton's laws, and we will then move into problems where that would have been much more complicated. Let's take a look at another example though. You may recall this problem from when we were talking about projectiles. I hope you do. It says the cannonball is fired horizontally at 308.0 meters per second, but how did that happen? If the 8 kilogram cannonball is fired horizontally at 308.0 meters per second, and the cannon muzzle is 1.90 meters long, what is the average force on the cannonball during firing? When we were doing projectiles, I told you to emphasize that the 308 meters per second is the initial velocity of the cannonball as a projectile. In this problem, however, we are looking at how the cannonball becomes a projectile. The 308 meters per second is the final velocity in this problem. I could find the average force using Newton's second law if I knew the acceleration, and I could find the acceleration using kinematics. But we want to emphasize again that we could also do this using the work energy theorem. So the work done is equal to the change in kinetic energy. The work done will be the average force dot the displacement delta x, and the kinetic energy change will be kinetic energy final minus kinetic energy initial. Conveniently, the kinetic energy initial is 0. The kinetic energy final is 1/2 mv squared, where we know the mass and we know the v, and the delta x is the muzzle length of the cannon. So we can solve for the average force like this. And I get 200,000 newtons, or 200 kilonewtons, is the average force necessary to accelerate this cannonball, as shown here. All right, we'll do more examples in class, possibly including some with setups more like this one, where the force does change over the distance.